In our last comparison, when we were looking at pre and post test scores, it seemed evident that since our averages for our post test was higher than our averages for our pre test, then we came to the conclusion that yes, they did learn after our lesson. However, it's not very scientifically accurate just to jump to that conclusion because you're going off strictly off the basis that the average was higher than the other average. And it doesn't always work that way because sometimes some students might have decreased, or you might get outliers of students doing extremely well and students doing extremely poorly. And this all is taken under consideration through things called standard deviation and standard error. And so what standard deviation means, as you guys can see here, well, first let's go over average. Most of you guys know what average is. It's just a sum. That's what this sign means. It's just the sum of all your x values or all your scores divided by the amount of scores that you have. And that's that. Standard deviation is meant to define the distance that your scores are traveling away from your average. And so if you look at what this equation represents, it's not just supposed to be a complicated equation. It actually has meaning. This is just saying that you take each of your average or each of your values, like this would be one value, another value, and you subtract it from your average value, which would be this value, and you just squared it. And then you divide that by the amount of trials that you have minus 1, and then you square root that. And all that means is that's just fancy talk for saying that we're trying to find out the average distance away from our average, which is kind of interesting to understand. You're calculating an average distance here. And so they set it up to a certain way to where 60, I believe, 8% of the data lies within one standard deviation plus or minus of the average, and in 95 of your percent of your data should lie within 2 standard deviations. 99 should lie within 3 standard deviations. But that's not exactly what we're going to be looking into right now. We're going to first let's try to calculate our standard deviation for our teacher 2. And in this comparison, I'm trying to keep them independent. So this trial is going to be, suppose a teacher 1 had a test score, like a major, I guess, tax score of 63%, and then this other teacher who was also working there had another tax score of, let's say, 73%. And this is just supposed to say the board is deciding on who to keep and who to fire, and they need statistical evidence of who is better. And so the way that they would do that is they take all these averages and they compare them. And so, but they also have to be sure of certainty. And so let's calculate our standard deviation, which you could go through all of these trials and subtract it by the average, square it, divide by n minus 1 for all of them. However, luckily Excel has come up with a fancy formula where all we just do is STDEV for standard deviation, and we just highlight our array, and our standard deviation is there. And so we're not exactly done yet, because we could have somewhat of a large standard deviation, but it wouldn't really represent anything unless we have a large amount of trials. If you were to just have a trial of 3 students versus a trial of 50 students, it wouldn't really be fair to compare that. Say the average of these 3 students was higher than the average of these 50 students. Well, that's not necessarily to say that all of these 50 students are worse than these three outstanding students, because you only took samples from 3 students. So this is what we call an error. And an error is basically defined as it's kind of like the standard deviation, but only it decreases with the amount of trials that you do. And so the standard error is defined as simply the standard deviation divided by the square root of n. And you guys can clearly see that as n, or the amount of trials, increases, the standard error should decrease. So ideally, you would like to get the smallest amount of error as possible by having the highest amount of trials as possible. And so we're just going to go our standard error, and we're just going to say that's equal to our standard deviation, which is this, divided by the square root, SQRT, of 20, which is the amount of trials that we have. And so that's our standard error. Let's fix these decimals as well. Okay. So now, it still didn't really tell us much. It still seems that our average is higher than the other average. So we're going to make another chart here. So we're going to do insert column. Let's do this 2D this time. Let's keep it simple. And so we're going to select our data. We're going to add in our series name. Let's call this teacher 1, and our series value would be the average. Okay. Our next one would be teacher 2, and our series value would be our average. Okay, and we don't want the horizontal axis to be called 1. We want it to be called, let's say, test scores. Okay. Alright, so we're done with that. Again, let's label or let's adjust our axes to be from 0 to 100. So we have a fixed value of 0 to 100. Alright. So now it still seems evident that our teacher 2 has done a better performance than our teacher 1, but we still don't know at what % likelihood. And so what we do here is we just take our standard error and we're going to click, so let's look at our teacher 1. We want to click layout, and we want to go, sorry, let me maximize that, and we want to go to error bars. We want to do error bar options, and it automatically wants to do an increment of percentages or just an increment of 10. We don't really want that because that has nothing to do with what we're comparing. We want custom values, and we want to specify that value to be plus and minus our standard error. This is for teacher 1, so we're doing standard error right here. And again, so that's positive. Our negative would be the same. Enter. Okay. And so what we see here is that our average value is 63, plus or minus a little wiggle room of certainty. And so we're also going to do the same thing for teacher 2. Let's say that that is, let's go to error bars, custom, and we want to say, okay, plus or minus the error. Okay. So as you guys can see just from this chart, that teacher 1 had an average of 63, plus or minus a little wiggle room. Teacher 2 had an average of 73, plus or minus a little wiggle room. But even with this wiggle room or this error, the errors still don't overlap. So I'm pretty darn sure that teacher 2, since the errors don't even overlap, the lower bound of this error and the upper bound of this error aren't even close to each other. I'm just going to go ahead and say that yes, teacher 2 has done a better performance than teacher 1, but we need a number to put with that, and so this is done by something that we call a t-test, and a t-test is where we compare two independent trials, or two independent, I guess, variables being teachers. And so we're just going to say our t-value is defined as the difference in our averages between the two teachers divided by the Pythagorean average of their errors. And I'll show you why this is the Pythagorean average in just a minute. And so what we're going to do is just plug that into what we have for our t-value. So we say equal to, let's keep this in parentheses, keep it neat. So our x bar 1 is just the average of our first teacher minus the y bar, which is the average of our second teacher. There. Okay, and then we want to say divided by the square root of the standard error of our first one squared okay, plus the standard error of our second one squared. Alright, and so there's our t-value. It doesn't really make much sense as to what this means right now. The actual derivation of what it means is done through quite a significant amount of calculus. If you guys are interested in learning it how, I would recommend taking the Statistics for the Sciences course. But Dr. Bott has been kind enough to provide us with a chart of preset data. And so what we say is, since we have a total of 20 students here and a total of 20 students here, that we have a total of 40 students. And degrees of freedom is typically defined as that amount minus 1. But since it's such a large amount of 40, let's just use 40. But even still, our table doesn't even go up to 40, so we're going to have to use 30. And so what we do is we look at the closest value of 2 or negative 2. It doesn't really matter what is negative and what's not. It just means that we compared our lowest with our highest first instead of our highest with our lowest. And so we're going to look at 2.8, which is all the way up here with an error, or with a t-value of 0.009. So let's say 0.009. And of course, let's convert that to percentages, like so. Let's increase the amount of decimals as well. Okay, and so that's the percent luck, which basically means that there is a 0.9% chance that this is not, that teacher 2 is not better than teacher 1. So there's a very small chance that he's not better than teacher 1. So that means there's a very likely chance that he is better than teacher 1, which is just defined as 1 minus that. So equals 1 minus this value. Okay, and so that gives us a 99.1% significance level. And since in science we typically keep it at a 95 or higher, if anything is at 95% or higher significant, then you do say that it is statistically significantly different. So I can say to the Board of Education that based on the evidence of this test and the statistical analysis of it, teacher 2 is significantly different from teacher 1, and I would recommend, I don't know, whatever course of action you need to take on teacher 1, whatever course of action you need to take on teacher 2. It has been proven here that teacher 2 is more effective. But the reason that going back to my reason of how this was defined for a t-test, I also want to talk about a z-test, which is basically the same thing, only it's not comparing two different teachers. It's comparing a teacher to, let's say, the national average, or a theoretical value. So a national average should have something, a trial amount of millions. Let's say the national average for the tax test being X amount would have an error almost non-existent, because our n value, of course, would be every student who has ever taken a tax test, which is millions. And so our standard deviation, no matter what that standard deviation was, divided by the square root of something so large, should be virtually 0. So we call that a theoretical value because it has virtually no standard error whatsoever. And so the reason that this difference was the difference of the Pythagorean average is because now let's suppose that our y bar is not our second teacher, it's our national average. And so our national average is being compared with our actual average. And since now our national average's standard error is now virtually 0, this t-value will then become the x bar, or average of our first teacher, minus the y bar, which is now our national average, over the square root of x bar plus something that is virtually 0. So that would just go to the square root of x the standard error squared, which is just the standard error of our teacher. So our z-value becomes the equation of x bar minus mu, which mu is just the national average or theoretical value of whatever you're comparing, and divided by our standard error of our sample. And so let's do that for each of our teachers. So teacher 1, let's say, is equal to the, let's keep it parentheses, keep it neat, the average minus the theoretical, or national average, divided by the standard error, enter. Alright, and so now let's try it for our teacher 2. Let's say that is equal to parentheses average minus national divided by error. And as you guys can see, that this z value is quite a bit larger than this value. The reason being that the average is quite far from the national average on this one, and the average on that one is actually pretty darn close. And so what we want to do here is we want to assign it certain percent values. And so what we want to say is, let's go to the chart that Dr. Bott has given us, our z-chart. Alright, So we want to look for a number that is 4.57. The reason that this one is negative is just because I had my lower value minus my upper value. It means the same thing because the difference is still the same. So we want a value of 4.57. Unfortunately, this chart that Dr. Bot has given us only goes up to 3. And as you guys can see, this value decreases as the z value increases. So all I can say for certain is that our percent luck on this trial is going to be less than, let's see, that's 0.27%? Yeah. Which means that our percent luck, let's say percent significance, is greater than 99.73%. That's supposed to be a percent, forgive me. Alright. And let's do the same for this one. Now, for this one, our z value was a 0.6, roughly. So let's say that our percent luck for this one, percent luck, and percent significant. Okay. So percent luck for this one is just, let's see, that this was 0.6, that's 0.5485. Alright, and it's already converted us to percentages. If it hadn't, it's just a simple click up here. So that is going to be, our significance is just simply 1 minus that value. Alright, enter. And so now we found our percent significance for both our teacher 1 and our teacher 2. And like I said earlier, the standard for science is that if it's higher than 95% significant, then you do say that it is statistically different, or statistically a significant difference. And so for teacher 1, obviously from, actually let me show you guys what this would look like on our bar chart as well. So let's add, select data, and we want to add our theoretical constant, or let's say our national average. Let's say national average. And that value was 75. Alright, so now that has been added, and like you guys can probably already tell, I'm not going to add any error bars because I already told you that the error on this is virtually 0. And so you guys can see from teacher 1, even with the wiggle room that's been allowed, it hasn't matched up to our national average. Teacher 2, our wiggle room has overlapped with our national average, so we could say, it might have been a luck thing that the national average was slightly above it. I mean, it's not significant by it's only 45% significance, which does not match our 95 or higher significant standard. So what I would conclude from this now is that teacher 1 was significantly different than the national average, significantly lower. Teacher 2 was lower, of course, but it wasn't significant. We could say it might have just been his off day. Maybe. And of course, the main question that we were trying to ask is which teacher, of course, had the higher score, which, based on the average and our t value, was by far teacher 2. And so we had a 99% significance level that teacher 2 was significantly more effective than teacher 1. And so this test is really used for a more scientific approach of analysis whenever you're comparing things, and it's much more I guess, professional than simply comparing averages and coming up with conclusions that way.